All right, so today we're just going to continue with arrays. We'll continue that throughout next week as well with some miscellaneous stuff. And then that takes us to the fall break. And immediately after you come back from fall break, that's your midterm. It'll probably end up being the same format as the first exam, but it'll end up being a little bit more, or worth a little bit more towards your grade. So keep that in mind. So we left off talking about dynamic collections in Java. They're great, right? Use them. Or if you have a choice between regular old arrays and dynamic collections, the choice is clear. Use dynamic collections. There are some instances in which you have to use arrays or 2D arrays or something like that, simply because you're using somebody else's code and that's what they've used. But in any case, we're going to see further advantages of those things. One of the big advantages is bookkeeping, right? In C, you have manual memory management. It falls to you, the programmer, to basically do everything, keep track of everything. You have to keep track of the size of the array, right, that you create, because if you ever want to pass it off to a function, if you want to pass an array to a function, you need to tell the function how big the array is, right? Because it doesn't know. Because it's manual memory management in C. Now, we're talking about C here, C, right? If you want to pass an array to a function, anytime you pass an array to a function, you also need to pass the size of the array, right? Otherwise, it doesn't know how to iterate over the array at all. There is no way in C to determine reliably how big an array is just given the array, okay? There are going to be some bad posts on Stack Overflow, and bad posts on just random internet C help forum and somewhere that are going to say otherwise, that you can use like some combination of size of and then arithmetic to figure out how big it is. No, those are only good for static arrays, the things that we started looking at the very beginning that we're no longer looking at here. Remember, with C, we want dynamic arrays, because static arrays on the stack, your stack is so small, there's no way that you're going to be able to store anything reasonably large. This is why we call malloc. Once we call malloc, then we can go ahead and use the array. If I forgot this, right? If I didn't have this at all, right? 5, 1, 2, 3, 1, 2, 3. There is no way for me to remember that. If I pass this off to a function, right, then I have to pass off a hard-coded value of 5 million, or I just have to assume that it's 5 million everywhere, right? That's not a good design, right? There is no way for you to tell after you've created it, just given ARR here, how big that dynamic array is. In order to do that, you would have to do some really deep level systems programming. You'd have to change basically the C language itself in order to get that information, right? In contrast, in Java, if I create an array, what do I use to determine how big it is? So int ARR is equal to new array int of, say, 100. I didn't put that into a variable. How do I get the size of the array? Do we remember? Size would be for dynamic collections, which we should use, but for arrays, it's going to be dot length, right? That's not a function. That's not a method. That's a property that you can then access to get the size of that array. Why? Because Java is memory managed, right? So already we're seeing, great, we have to, a lot of this stuff in C has been taken care of for us in Java, right? You have to ensure that there's no illegal undefined access errors. If you attempt to access something that is beyond the scope of your array, it could result in a segmentation fault. It could result in garbage values. It could go completely unnoticed, right? It is a completely undefined behavior. So you have to make sure that you're not going to negative index values, that you're not exceeding the size of the array, et cetera, et cetera. Not only that, but again, you have to free it up, right? You need to make sure that you clean up your memory once you're done using it. Put away your toys, right? Check in your library book so that the operating system can use it for some other process or give it back to you if you need more memory, right? And the way that we do that again was, what was that function at the very end? free, right? You free the array. There it is. We give it back. We'll demonstrate more Valgrind examples later on. Right? In fact, you'll see a memory leak in your lab next week. Once freed, that memory no longer belongs to you. Attempts to access it are undefined behavior. You can't give it back and say, oh, ooh, whoops, no, I actually meant I needed that, right? There's no going back, right? There's no undelete. Consumer products, like computers, desktop computers, operating systems, stuff like that, with nice graphical buttons and stuff, those are intended or designed around human error because it's human-computer interaction here, right? This is way less forgiving because, well, it's assuming that C programmers are no mere humans, I guess, right? But they still are, and they still make mistakes. But that's the design of the language, right? You cannot, once deleted, you cannot go back to it. Attempts to free memory that doesn't belong to you. Attempts to free memory that doesn't belong to you are undefined behavior, right? So let me go over here. Let's go ahead and create a static array instead. Int array is equal to the first few primes here, 3, 5, 7, 11, 13. There we go. Right. Now, where is that memory located? Because I did it statically, on the stack, right? What if I try to free up that array? Right. Now, that does belong to my program, right? My program owns its own stack memory. But don't go messing with the stack memory. What are you doing here? You've got your stack of dishes and you say, oh, okay, I don't need those dishes anymore. Right? You're a running program. Of course you need those dishes. You need that stack frame. If you end up freeing your stack frame here, it's probably going to be, hopefully we get this nice message called a stack smashing event. Let's find out. GCC demo. Yep, a warning. It's such a warning here that I didn't have to even use the wall flag here. It's saying, do not do this, right? Let's see what's happening. There we go, segmentation fault. You know what? The stack smashing event was from the old CS50 IDE last year. I don't know if this is configured to detect and report stack smashing events or not, but whatever, it results in the same thing. It dies because of a segmentation fault. Here's your stack frame. Go ahead and delete it or give it back to the operating system. That means that how can you return from a function? How can you call another function if this memory is wiped and gone away? Right? If you have a random memory location, let me get rid of this. Say int star ARR is equal to 42, right? I'm going to set this equal to some stupid random memory location that probably doesn't belong to my program. You can't free it up. It doesn't belong to you, right? Segmentation fault. So all of these events are things that you need to be careful of and be and not do, and basically just be careful. Right? And unfortunately, it's all manual. A failure to clean up memory properly leads to memory leaks. There we go. In C, you need to be good stewards of resources, okay? And again, what I mean by that is you just need to do things properly, right? If you allocate memory, you need to free it up after you're done with it. You need to make sure that you're not stepping on memory that doesn't belong to you, right? Using static analysis tools like the wall flag and the compiler and listening to those warnings, that will take care of the good majority of problems. Using Valgrind as a secondary dynamic analysis tool will allow you to detect what else is going wrong there. Right? I don't want to do it here because the CS50 IDE is extremely limited in what you can do. So what I'm going to do is I'm going to go and show you, I wanted to show you a memory leak on Monday, but we ran out of time and I couldn't do it on the CS50 IDE because they're very, very stingy. Let's see, is it more foo? Oops, foo. Yep, there we go. No, that's not right either. More test 2. That's it. That's what I wanted. So let's edit this file here. Actually, let's just walk through this file. So this is not a static array that can hold 5 things. Oops. Why was that? There we go. It just messed up really quick. So for 1,000 times here, what I'm going to do is I'm going to call malloc, and I'm going to allocate space for 5 million integers. Okay. Now, how big was that again? 5 million integers times 4 bytes each is roughly 20 megabytes, thereabouts, just short of that. Do something with it. And then I'm going to sleep for 1 second, because if I don't sleep for 1 second, this program will just go really, really fast, and it'll immediately die because the operating system will say, you stole too much memory. I'm going to kill you. All right? There are limits on basic processes on the CSE server here. So I'm going to sleep for 1 minute. I'm only going to steal 20 megabytes every 1 second. Right? This is sleep for 1 second. By the way, do not put sleep in any of your programs. Right? I'm intentionally slowing my program down here so that we can see it. Right? Don't intentionally slow down your program for no reason. Okay? GCC test 2. Right? Yeah. Don't worry about it. All right. So if I just run this, of course, it's just going to run in the background, and I'm not going to notice anything. So let's kill that. I'm going to run this with an ampersand after it. What that does is that says, launch this program in the background so that I can continue here on the command line. Right? It was launched. It has a process ID of 51554. Right? I can list all my processes. PS is short for processes. There it is. It's running. Right? And I can use another tool called HTOP here. This is another reason I want to use CSE instead. It's because it's got a nice HTOP implementation. The CS50 IDE does not. So you can see here that there are 64 cores on this computer that's running. It used to run here in the basement of Avery. They've moved it over somewhere else. I have no idea for security reasons, for network security reasons. But in any case, I don't know where the hell it's running anymore. But we can see that there are 64 cores. Whoever's using core 28 right now is using 100% of that core, right? So maybe the fans are going off in there or something, right? I'm going to, where's my process? So user, cburk, there we go. Where is a.out? There it is, 51544. Hey, look at that virtual memory. Those are megabytes. That's what the big M stands for. We're already up to 1,300 and, well, now 1,400 megabytes, right? Why? Because it's been running now for maybe a minute or two. It keeps stealing more memory, right? Now we're up to, what would that be? 1.6 gigs, right? And it just keeps going up. Every second it goes up by 20 megabytes, right? Now imagine, now this is an extreme example of a memory leak because it was intentional. But imagine, just small little snippets. A little bit of memory here, a little bit of memory there, a little bit of memory there. But on an operating system that is meant to be running 24/7 for weeks, right? Or in perpetuity, right? If you've got an error, a memory leak like this, it will eventually manifest itself down the road, right? Rather than immediately here. So I want to stop that. It looks like we were wasting about 2.5 gigs so far. Don't worry, it's got some to spare, right? There we go. It has 126 gigs of memory, right? We priced out that DIMM in the other class. Somebody found a DIMM, double inline memory, right? Everybody's built their own computer or not, or at least opened it, cracked it open and looked inside a desktop computer? No? Okay. If not, then come to a coding event in December, and we have just junk computers that we let the kids rip apart and play around with. But anyway, we priced out a DIMM. I think that somebody found a 512 gigabyte DIMM for $2,000, right? That's how, so. I mean, you could get that much memory for far less if you were willing to put it into multiple DIMMs. Anybody buy memory recently? All right, what did you buy?
Just maybe stick from the laptop.
Oh, okay. So like a stick memory. Okay. Yeah, this is RAM right here. This is and you can't download more of that. So yeah, there we go. All right, let's go ahead and kill this. Kill 51552. That is going to end my process. Right. Oh, looks like it looks like it was killed anyway. Oh well. Yep. Oh wait, no, I mistyped it. 554. There you go. Wait, which one? 51544 is the process that I needed to kill. There we go. Now I killed it. Now let's go ahead and edit this file and show you what a good steward of memory you can be by freeing it up immediately after you're done using it, right? So that you don't have this memory leak. GCC, yeah, whatever. A.out in the background here. Let's go back up to htop. Let's look at my user process here. There it is, A.out at the very bottom here, right? And we've got, there's a virtual memory, which is not even up to the megabytes yet. That's kilobytes. And we've got 24,000 kilobytes. That's roughly about 20 megabytes. Right? Is it changing? Nope, because I ask for some. Here's your 20 megabytes. Give it back. Ask for it. Give it back. Ask for it. Give it back. There's no memory leak here at all. And Valgrind will tell you so, right? Kill 53020. Right, there we go. And let's go back over here to the bad, buggy version of this program where we don't free it up. Compile that for Valgrind, right? Remind me, what do I need to do if I'm going to do this for Valgrind? I've shown Valgrind before, right? Okay. So what was that flag? -G in order to preserve line numbers here. Right? Let's run this through Valgrind. A.out. Oh, actually, you know what? Let's also take out that sleep because I do want this to run very, very quickly, right? There we go. And let's not be so greedy. Let's only go, I don't know, 10 iterations here. There we go. And GCC. And now let's run this through Valgrind. And Valgrind will tell us, you did something wrong. Oh, come on. Okay, there are no errors and no context, but guess what? We've got a leak, a memory leak, right? How big was it? Well, there were 10 blocks with a total of 200 million bytes. 20 million bytes each times 10, that's where that comes from. And it's telling us that it was definitely lost. You never cleaned it up. You had a memory leak here. Let's go back and again fix that. We will take out this comment, and now we're freeing it up. When I run this through Valgrind, it's going to come back with no bytes were lost, right? 10 allocations, 10 frees, you're good. Right? No leaks are possible. Oh, thank you. Good. It's not even possible that you screwed this up. It's so good to hear that kind of affirmation from a computer, right? All right. So, what about Java? Right? Java. No memory management. It is all taken care of by the Java virtual machine's garbage collector. Right? The garbage collector is a part of the Java virtual machine that runs periodically in the background and monitors all the memory that you're using in the Java virtual machine. And it sees, okay, you allocated 20 million bytes over there, and nobody is using it, right? No, because there's no references to it at all. That's eligible for garbage collection. When I feel it's best, and I'm the garbage collector, when I feel it's best, that is, it's worth it to clean it up, I go over there and deallocate that memory and reclaim it for the Java virtual machine. Right? The garbage collector takes care of all of it. Right? Once an array is no longer in scope, once you have no references to it, it's eligible for garbage collection, and at certain increments, the Java virtual machine will claim automatically. You don't need to worry about this. You mostly don't need to worry about this. There are some instances where you can write bad Java code that bad Java code itself is greedy and it hoards all these references, right? So you can get a memory leak in Java if you write bad Java code, but you have to basically go out of your way to do it, right? As long as you're not intentionally writing bad Java code, you can mostly get away with it. And there's no bookkeeping. Right? You can use, array.length or say list.size to determine how big an array or collection is, right? So, lots of your problems are solved. Don't think that doesn't mean that you don't have other problems, because it does, right? There's a term, no silver bullet. Have you ever heard of that term? Right? And there's no silver. It's used in a lot of disciplines and contexts. There's like a silver bullet kills the werewolf, right? That's the solution, the one and only solution. There is no silver bullet, right? You can come up with a programming language that manages memory 100%. It just comes with its own quirks. It comes with its own disadvantages. The disadvantage here in Java is that you pay a potentially huge performance hit here in terms of efficiency. Why? Because you've got this Java virtual machine that you're built on top, right? So you're even further away from the hardware. You're paying for that. You're paying for this additional garbage collector to walk around to make sure that memory is managed. You're paying for all of that in terms of efficiency and performance. Right? You're not writing system level stuff in Java, trust me. Right? Okay. And certainly not writing system level stuff in, oops. Nope, sorry. I almost killed the live stream accidentally. All right, so questions so far on any of this? No? All right. Let's talk about multi-dimensional arrays. So both languages support multi-dimensional arrays. Right? 1D arrays are regular old arrays. Right? You've got one dimension. You work in one dimension. Right? It's like the line, the x-axis line, the number line, except that it only goes one way. You can have 2D arrays, which you can interpret using rows and columns. Right? Or another way of looking at 2D arrays, you've got rows and columns. We call those what? Tables. Right? And now I'm going to do a poll here, an informal poll. What else? If you've got just numbers, if you've got rows of numbers and columns of numbers, what is that thing called? I heard it. Matrices, right? So the informal poll is, there's another computer science one. It's for engineers, and the major part of it is linear algebra and matrices. I'm like, the typical freshman, no, this is different because this is an honors section, but I thought the typical freshman probably hasn't done a lot of linear algebra with matrices. Certainly not, have you like inverted, you've seen matrices, yes? Right? Have you inverted matrices? Oh, okay. Have you had linear algebra then?
Right now.
Oh, right now. Okay, that's cheating. No, but the typical freshman is not going to come in. Have you done eigenvalues yet? There, I gotcha. All right, good. And so they were saying, oh, this is supposed to be a computer science 1 course, and oh yeah, we compute eigenvalues, we compute matrix inversions, et cetera, et cetera. I'm like, freshmen haven't seen that stuff yet. Those probably are not the kind of exercises that you want to give them, right? So anyway, you have 3+ dimensions. You would think of those as cubes, right? Now we would call those rows and columns, but then in the 3rd dimension we'd call them aisles. Rethink what you are doing, right? There's probably a better way of modeling the problem that you're trying to model here. 2D arrays make sense because it's tables, matrices, those are all over the place. But 3D stuff, 4D stuff, 5D stuff, you're probably wanting a different model. You're probably wanting a different way of solving that problem. So we're going to stick with 2D arrays and 1D arrays only. Okay. Let's go with the easy language first. Let's go over here to Java. I want a 2-dimensional array. So create a 2D array of integers that has dimensions, say, I don't know, 10 by 20. Let's keep it small. 5 by 10. There we go. All right. So all you need to do, well, here's a regular old array, int array, right? Well, that's 1 dimension, right? One pair of square brackets there. If you want 2 dimensions, guess what you do? Oops. 2 squares, right? If you want 3 dimensions, you can do that. 4 dimensions, 5 dimensions, you can do as many dimensions as you want, but we're not going to do that, right? We just want 2 dimensions here. New int, and then you have to specify the dimensions. We want a 5 by 10. In other words, 5 rows, 10 columns, right? So 5 by 10, and you're good to go. Now, I told you that if you have a choice between a traditional array and a dynamic collection, you go with the dynamic collection. What that would look like, though, in this instance, is going to be a list of integers. You can do that, right? You just have, Langle, Wrangle, Langle, Wrangle. You've got this nested thing. It's kind of unwieldy. Don't worry about it, right? If you just want to do a simple matrix, a 2-dimensional matrix here, you could stick with a regular old traditional array. Okay. Once you have that, you can specify an entry using 2 dimensions, 2 indices. So, for example, and this is not an array anymore. Let me rename it. In fact, array sub. Let me hold off on that first. This one is at the upper left, right? So this is set the upper left value to 42. There we go. Why is it at the upper left? Because you start your indexing at 0. 0, 1, 2, 3. 0, 1, 2, 3. And so you need 2 of these dimensions to specify 1 element. Okay? What about the last? That's up at the upper left. What about the one at the lower right? Array sub what is equal to 101. Set the lower right value to 101. Where's that going to be? Where's the last row? 4. And then where's the last column? If there are 10 columns, 9. Right? This is known as row major form. Row major form. Right? The row is the first index. The column, the second. Okay? And then, of course, you can iterate over these things. For int I equals 0. I is less than array.length I++. Okay? For int j is equal to 0. J is less than array.length j++. I'm going to do a nested for loop here. For each row, right? For each row. For each row. For each column. But can I use the same value here? If it's a square matrix, 5 by 5, 10 by 10, sure, I could do that. But this is not a square matrix. It's 5 by 10, right? It's a rectangle. I can't use this value here. Instead, what do I need to do? I'll use this. The ith row, how big is that thing? What is the length of that thing? 10, right? Now, you can put these into variables if you want. You can save them off. This is a good pattern to follow because it does protect you against multi-dimensional arrays that do not have uniform dimensions. What I mean by that is you could have an array where the first row is 10 elements. The second row, for whatever reason, only has 3 elements. The third row has like 5 elements, right? The last one has 1 element. It's all over the place, right? That is possible. It is not recommended, right? Why would you do something like that? That's weird, right? You probably have a use case for that there's a better solution for it, okay? Once I've got that, I, of course, can print them out. Printf, or system.out. System.out.printout. Printf, let's say. %d space, and array sub I, j. There we go. And then at the end of the row, let's go ahead and system.out.println. Let's print an n-line character. Not ln, but printf. Right? And maybe at the end of the row, we'll print this nice, square bracket. At the beginning of the row, we'll go ahead and print this nice opening square bracket to get a nice looking matrix here. So what is it going to look like? It's going to look like 5 rows with 10 columns. And the upper left one will be 42, the lower right one will be 101. What about everything in between? Do we remember what the default value in Java is? 0. There we go. Upper left, 42, lower right, 101. And it is 5 by 10. If you wanted to align this stuff a little bit more, a little bit better, you could say 4D. Right, there we go. Now we look. Now everything lines up. Nice, right? Okay. Remember I said I wanted to rename that variable because it's not really an array anymore, is it? What is it? It's a table. Table. Oh, okay. Now I have to rename everything. Table, 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 table. No, there's a better way. This is why I stopped myself from renaming it, because I wanted to take this opportunity to show you a cool tool. I don't know if maybe I've shown it before. Right click any variable, refactor, rename, table, and they're all done for you. Right? So there's yet another IDE tip that will help you out. Over here in VS Code, at least the web browser version, I don't think it's in there. If you have the desktop version of VS Code, I'm sure that there's something like that. Okay. Cool. There's your 2D array experience. By the way, in Java, do I have to clean it up? Nope. It'll be taken care of for me. So here's a Java example. Java. There we go. Put that in the notes for you. What about C? Right. How are we going to translate this stuff here in C? Right. Let's take it over here to our coding environment. Okay. So let's create a 2D array of integers that has dimensions 5 by 10. This syntax is not correct in C because you do not have the new keyword. How do we do one single array here? It's going to be int star array, right? And I would make a call to malloc, int star malloc. I would ask for a certain number of bytes. If you want, say, 5 you want 5 integer, or on that first row, for example, if you want 10 integers and each integer takes size of int bytes, that's what you're going to want. Already I'm off track here because I'm hard coding this value 10 here. Maybe it was 5 instead. I don't know. Let's start over. Let's keep track of those dimensions first of all. Usually we use n, and if we have 2 dimensions, we use, well, what comes next? M. What comes next? Int. LM and, oh wait, that's already backwards. So L, sure, let's go backwards here, right? That's why we don't like 3 dimensions, right? Then we run out of things. But N and M are typically used for the number of rows, the number of columns. If you want, instead you can say num rows or num calls, right? Now I abbreviated the second one simply so that these 2 variables would have exactly the same number of characters, right? And they would line up nicely. You could, of course, go ahead and columns, right? And then I was trying to look at it yesterday about what the style that does this is, where you, if you have a bunch of variables and initializations, you line them all up with the equal sign like this. Does anybody know what that style? There's a term for that, and I could not find it. Okay, all right. So some research for you over the weekend there. What is that style? Let's go ahead and go with num rows and num columns. I'm not going to be able to use regular old malloc here. Instead, what I'm going to have to do is hopefully this shows up on the live stream. Okay, I can get away with it here. So what I want is an integer pointer here. This is going to point to one array. All right, we'll do a visualization of this on Monday when I've got better visuals tools on the computer instead of the whiteboard here. Right, that's a 1D array. Right? What if I wanted a second row? What would it look like? Something like that. Right. What if I wanted a third row? Something like that. Right. Right. Dot dot dot. What if you wanted 5 rows, right? However many rows you want. Int star, there we go. and this is num rows. Right? Okay. That's great, but I need to manage all these things over here. Right? And I wasn't just circling it to draw your attention to it. Let me separate these things. Dot, dot, dot. What is that? It's an array. Right? An array of what? Array of arrays, we call them things pointers. It's an array of pointer, pointer, pointer. Right? So I need a reference to that. Except that it's not a pointer anymore. It is a pointer to pointers. So if 1 star gives you 1 dimension, 2 stars gives you 2 dimensions. How would you do 3 dimensions? Yeah, you guessed it, 3 stars, 4 stars, 5 stars, don't do that. Right? So what I need is an int star star. Right? And I'll call this table instead, right from the bat here. I'm going to call malloc, and I'm going to ask for a certain number of bytes. I'm doing this thing right here first. How many do I want, first of all? I want num rows. So, num rows times, now how many bits, or how many bytes, excuse me, does each one of these things take? What if I were to write the exact same code that I was writing before, size of int? Right? That will give you the number of bytes that an integer takes, 4. But are these integers? Nope. They are integer int stars. They are pointers. So, how many bytes does an integer pointer take? Size of can do that too. Right? That creates this array right here. Right? And I need to make sure that that I am typecasting this correctly. The thing on the left-hand side, whatever its type is, that is the typecasting that you should do on the right-hand side. Okay? Now, once I've set up this thing right here, I need to go through each one and set these up. So that's going to be a for loop. For int I equals 0, I is less than num rows, I plus plus. I need to initialize, allocate the ith row. And that is just our regular old friend malloc. The table sub I is equal to a call to malloc, int star, malloc num columns times size of int. There. That sets it up for the first row, the second row, the third row, dot, 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 until I get down here to the last row, the in general, the ith row. Okay? Once I've done that, then I can specify an entry using the 2 indices. There is no change here in the code at all. You specify 2 dimensions. There's the upper left, there's the lower right. It is still row major form. The row is the first index, the column is the second. I don't have table.length. What do I have? Num rows. I don't have table the ith rows length either. I have num columns. There we go. And I don't have system.out.printf. I just have printf. But otherwise, it's remarkably the same. Right? There's almost it's certainly a line-for-line translation here, almost, right? Except that I had a little bit more to do here because I have to do my own bookkeeping. Right? It's not simply a matter of a one-liner. Give me a 5x10, right? No, it's give me an array of integers, and then I'll go ahead and allocate them all for you, right? Now, if you did consider these 5 lines of code so arduous, all right, fine. Go ahead and put them in a function, and we'll take a look at how to do that next week, right? And then reuse that function. So, GCC demo. Let's make sure that I didn't make any mistakes there. There we go. And let's run this. It should print out the exact same matrix that we had before, and it does. There we go. 42 at the top, 101 at the bottom, except that I got lucky. How did I get lucky? They were all zeros otherwise. Is that going to be true in general? Nope. Bump this up to 500 and bump this up to 1,000, 10,000. Jeez. Let's see if this runs. All right, we're getting really, really lucky here. Or maybe I don't have the eyes for it, but they're all zeros, it looks like to me. There's not really a guarantee of that, by the way. Right? We've seen examples where there was garbage before, right? So, careful. Careful. Though it may look like they are all zeros, there is no defined default value for array or table entries. I'm going to kick this down to 5 and 10. There we go. Yeah.
If there's no set value, why is it so consistently zero? I mean, not consistently, of course. But
Yeah. Why is it 99% of the time zero? It's our good friends at the GNU people, whoever wrote the compiler, thought, okay, well, I don't have to do this, but I'm going to go ahead and do it because reasons. Because it seems like a good idea. And it is a good idea. And in fact, it's such a good idea that there's another function called Calic that does exactly that. Right? So there's malloc, there's Calic, there's realloc, there's realloc array, right? So there are a bunch of other things that you can use. The main difference here is that Calic, there we go. The Calic function allocates memory for an array. You have to call it a little bit different because I think that there are 2 arguments there. The memory is set to 0, right? There it is. So it is there. The default is 0. I don't know if if one is more efficient than the other or not. I imagine that it does take a non-trivial amount of work to go through and make sure that everything is zeroed out. If that's worth it, then do it. But you're going to pay a little bit of a price for it. Malloc is probably is a little bit more efficient in that, well, here's your memory, I don't care. Here's your memory, I don't care. Right? So if you want to, you can use Calic, just read all about it. Right? All right. Except that if I ran this through Valgrind, what kind of report am I going to get back? Did I free anything up? Nope. Wow. 241 errors. That's probably me going through and accessing stuff that is not initialized. But in any case, whoa, yeah. Very, very similar. Where's my heap summary? There we go, leak summary. 40 bytes in 1 block, indirectly lost 200 bytes in 5 blocks. Right? 240, what is that all about? 200 bytes, where does that come from? How big is our array again? 5 by 10, so that's 50. That's close to 200 if we multiply by 4. Right. All those bytes in that matrix are lost. What about the 40? Where does that come from? That's the rows. How many rows do we have? 5. Right? How many bytes apparently does an integer pointer take? 8. 8 times 5 is 40. That's what we're losing right there. Those are definitely lost. This thing right here is definitely lost. This stuff is indirectly lost. So let's go back and be good stewards of our resources. Let's go ahead and free up that table. This is not going to work. And we're going to see from Valgrind why. That 40 went away. The 200 remains. Why? What did I end up doing? If I deleted the table, what do? That's gone. I cleaned that up just fine. What about all that stuff? It's still there, right? So if you create this one, and then you create each row, and you want to clean them up, in what order should you do it? Reverse order, and then clean that column up. So instead of just cleaning up that table, let's go ahead and go into a for loop here. For int I equals 0, I is less than num rows, I plus plus. We will free the ith row. Free table sub I. And only after you're done freeing up each one of these, gone, 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 gone. Now it's safe to erase this one over here. And when I do that, oops. Let's run it through Valgrind to get a full report. Ah, excellent. In use at exit, 0 bytes and 0 blocks. Yeah, I like that. All heap blocks were freed. There are no leaks possible. Right? So you want to hear that all the time if you're programming in C or if you're a plumber or whatever. Right? All right. Any questions? No? Yeah, go ahead.
Can you show your code?
Sure. And don't worry, I will go ahead and make sure that you've got it in your notes as well. All right. No questions? All right, well then have a good weekend. It starts early. Games tonight, right? All right. It's an away game though, right?
Yeah.
Okay.